Hello everyone and welcome back to the good stuff that we have been doing. Today in this video we're going to prove this interesting property for periodic functions. Yes, it says that the integral from 0 to nt plus a, where t is the period of f of x dx, is equal to n times the integral from 0 to t of f of x dx plus the integral from 0 to a of f of x dx. Now we know periodic functions, okay? Just like the sign, we know that the sign for periodic function, the sign of x plus 2 pi is basically sine of x. And the reason that we say that once you get from 0 and you move all the way to pi, and then you come from pi up to 3 pi over 2, and then you move from here to 2 pi, if you continue this movement again, you're basically repeating yourself. So if you have any value of x, which is, let's say here is x, if you run back and come back after 2 pi revolution, you still end up with this value of x. So this is why we say sine of x plus 2 pi is equals to sine of x. So basically this is true for all periodic function. Now let's look at in detail here that this general theorem says that when you have integral, this is only for just a function. When it's an integral and the period is part of the argument for this, it's part of the limit of integration here. It says we can break it down into two smaller intervals where one of them features the period, and this is very a useful result. And let's see how we can prove it. One thing you should keep in mind is that for periodic function f of x, let's say it has a period t, so f of x plus t would equals to f of x. Now let's say we have f of x plus 2t, well that would be just f of x plus t and then plus extra t. Notice that because of an extra t, this will basically be just f of x plus t, and because of this t, this is basically going to be f of x. So if we continue this pattern, f of x plus nt is basically going to be called f of x, and this is a very crucial property for periodic function. In fact, this is basically true by definition, but it's going to be used to actually establish this result. So let's start with the left hand side to begin with. We have the integral from 0 to nt plus a of f of x dx. Now this integral, now what we need to do is that we're going to write it to an integral from 0 to nt plus the integral, I have to write f of x of nt of f of x dx plus the integral from nt to nt plus a of f of x dx. Now, having had this in our hand, now we're going to just, okay, no, we don't, no, what? Yes, we are correct for breaking it down. So what we're going to do is that on this part here, we're going to break it down into n smaller intervals, because we are going from 0 to nt. So basically this is equal to the integral from 0 to 1, from 0 to t of f of x dx plus the integral from t to 2t of f of x dx plus the integral from 2t to 3t of f of x dx, plus you can go further, you have the integral from n minus 1 t of f of x dx to the integral of nt of, yes. So next, so we would have, say, okay, let's say, yeah, so this will be plus, we can bring this down further. This will be nt plus a f of x dx. Now what do we do now? We are taking the sum from 0 to nt, so we can write this as a summation notation. So as k runs from 0 to n minus 1, so you have the integral from kt, I think kt, yeah. So you have kt here, so you have a kt and then a k plus 1t. Let's see if it is actually true, because if you have a kt, k is 0, you start with 0, and then if k is n minus 1, you end up with nt. So we are correct of f of x dx. Now this is equal to the integral of nt to nt plus e of f of x dx. So we're going to make some a good substitution here. What we're going to do in this part is to come and just set, let's just set x to be nt plus u. Notice that in this case dx equal du. Okay, now if x is nt, u will be 0. For this case, u will be 0 if x is nt. Now what happens when x is nt plus a? Then in that case, u would equal a if x is nt plus a. So you have this part runs from 0 to a of f of what? Nt plus u du. Now what about this part here? Let's bring down the sum. This is from k equals to 0 to n minus 1. And now for this part here, what about when this is x though? What about when x is kt? When again u will be 0, so you have integral from 0. What about x when kt plus 1? Well, in this case you have a kt plus t equals to let's say kt plus u. So in this case the kt is cancelled out, so u would equal t. So you have the integral from 0 to t of f of here you have kt plus u du. So now the problem has been simplified, so we could end up with something like this sum as k runs from 0 to n minus 1 of just the integral from 0 to t of f of u du, because it is a periodic function, and this is the integral from 0 to a of f of u du. Now this sum is the only problematic stuff, but it's not really an issue because this that nothing here depends on k, so we can actually pull it out. So if we look at the sum as k runs from 0 to n minus 1, there's no argument here. Okay, so we are basically adding n times 1 n times. So this is just 1, so this is just going to be 1. You are going to add 1 n minus 1 times. Okay, so you starting with 0, so basically you have n ones to add up. So this sum would equal n. So you would only have n multiplied by the integral from 0 to t of f of x dx plus the integral from 0 to a of f of x dx. And this is what we are required to prove actually, and it has been established. This result has been established. So thank you for watching, and please subscribe to the channel. Bye.